All right, cool, thank you.
No, I'll put it in the back somewhere. If I can find it.
Just remind me, like, where you
I'm using your charger, Andres.
No, but like when you stop using it.
Andres, I'm currently using your charger.
When you stop using it, so I remember to go.
Oh, that's not yet, Andres. I'm still using your charger, Andres.
Oh yeah, we should.
At least he's rolling the R.
What time? Hey, my friend recommended me some electric charge.
I'm in a very expensive my legs.
Is this Hispanic era?
Boom, yes!
Bro, what time is it? It's lit up.
Oh, that was so natural.
Yo.
I'm actually a boss. I'm actually a boss that spends 10 years.
Oh yeah, you're right.
Hola! You see some freaking.
There was something that came up at office hours that was very useful for people for visualizing spherical coordinates. It works better if you listen to the sound in your mind of Morris rapping. But this is for spherical, tracing out some spherical. This is getting lyrical. This is our x, y, z axes, and this is, if this is spherical coordinates, what does this represent? Yeah, let's do this off. So this is which variable? Rho. Okay, cool. Now people say, wait a second, Christian, you're using r in spherical coordinates. Sometimes in mainstream you're going to see r used for rho. I find that to be an abomination. We're not going to do that. But I do want to know what r is in this world. So z is this. If this angle is phi, what's this? Rho cosine phi. Okay, which makes this? Rho sine phi. Yeah, rho sine phi. Watch out, which is r. This PVC pipe, who was it that pulled it from the rubble? Was it you? Someone pulled it from the rubble. Oh, it was Vaughn. All right. That here, this length, we agree it's rho sine phi. Okay, well, this is just a line from the z-axis. And if you look at this all the way down, what is it? R. It's r. Okay, cool. So worth checking out. I realize that not everyone can see here, so I'm going to hold this up again. Here's rho. This length over here is r, because if you take this, you project it down, you got your r. Okay, cool. And then you know x is r cosine theta, that's theta. You do your usual trigonometry there. Okay, excellent. So that, having said that, today we are going to embark on a journey to something a little newer. We're going to kill a dimension. We're going to kill two dimensions actually. We're not going to triple integrate anymore. We're going to do single integrals, but in a way that perhaps you've not seen before. So to do that, I'm going to need a couple things. Okay. Oh god. I was walking down the hall and these buttons just kept activating, so I'm just walking going dx, dy. Tourists thought it was just another normal day at MIT. Okay. We're going to talk about vector-valued functions in a particular context. This is what's called a vector field. We need to bring a projector screen down. So far, we have been talking about, for the most part, scalar valued functions. What is a scalar valued function?
Cartesian.
Cartesian,
A
polar,
function that
spherical.
gives you a whole number.
Anything gives you a full number. Yeah, a whole number, be careful, because I'm thinking integers or something. But yeah, so give me an example of a scalar valued function, x squared plus 1. Or if we go up to 3 dimensions, right? Z is equal to x squared minus y squared. Hey, it's a Pringles chip. Otherwise known as a hyperbolic paraboloid, otherwise known as your pants. A saddle point. Okay. What we're going to do now, though, is make it so that at every point, instead of getting each point to give us a number, for example, 1 on x gives us 2 as a result, here 1 on x, 1 on y gives us 0 as our result. We are going to start outputting not scalars, but vectors. And this is the notion behind vector fields. You've seen them in high school if they ever had to do the whole Newton's method, what have you. Who has never heard of a vector field before? This will be fun. Like a slope field. That's exactly it. Remember slope fields? In fact, let's go one step further. X squared plus 1, right? What's the derivative of x squared? 2x, right? So what if I made a slope field to show the derivative of this function at every point as a vector? Now attempting to do that using following. Let me just copy the syntax. Okay. And actually, I have a better idea. I believe I've got fields. Okay, cool. Very nice. Okay. So here's a field. 1, 1. This is a vector field whose x component is 1 and whose y component is 1. Written as a field, that would be, or notationally the same as 1, 1. At every point. All good? Okay, let's make our field now. Give me something wonky here. Sharifa, give me a function of x and y. 2x cubed, very daring, plus y. Okay. What do you want the y components of the field to be? Wow. Exotic. What does this mean in English? This is going to give me a field of vectors. At every point x comma y, the x components of the vector is going to be 2x cubed plus y, and the y components of the vector is going to be y over x. So let's do that. I think this will be fun. This is like super dark one. I can't even see this. This is what? 2x cubed plus y, and this one was, what did we say? That's pretty cool. That's pretty. Okay. Excellent question. Blue is low value, red is high value. And I think it's
That's because they can't stretch out the arrow, so they need to use constant.
exactly. And is it about magnitude? And, yeah, it's just about magnitude because think about it, the direction is shown by the arrows, right? So that's where we are. Okay. What's another example of a vector field? I don't know. Pick something a little less exotic, but maybe more relevant to, like, I don't know, physics. Physics, anyone?
Of course, yes.
Okay, I heard David's voice. David has been activated. All right, give us a field that you like from physics. That is, you're not going to break the bank.
KQ over R squared R hat.
Okay, I like that. KQ over R squared. What am I saying? Yeah, over R squared R hat. Let's write this in Cartesian so I don't have such a hard time plugging it into this. What's this? This is KQ. This is just a number, so let's just call it 1. Okay, over x squared plus y squared. And r hat is our direction. What's the radial direction?
X and Y.
Yeah, let's just do x, y. Does that make sense to people? That points.
Wait, over its magnitude, it's r hat.
It's r hat. Oh yeah. Okay.
Yes.
I'm going more for the direction, but this is exactly correct. You're right now. Okay. Does everyone see how this is more or less that behavior? Okay. It's got a radial direction, and it's got some constants. So let's plug that in. So the x components of the field. Oh, and this is going to be this is x squared plus y squared, square root of x squared plus y squared. What's that? To the 3 halves. Okay, so let's plug that in. So the x component is x over x squared plus y squared to the 3 halves. We'll copy that over here and make it y instead. Aha! You will recognize that?
Yeah.
Radially outward, right? What if you were an E&M and you wanted to be the attractive charge? Negative. Now you're radially inward. Okay. Again, at every single point we are defining a vector. Before we do any math about this, this is really useful to, like, kind of paramount. to have a sense from. Are people good with this? Do you all see how this could work in 3 dimensions? See how it would work in 3 dimensions? I would like to volunteer so that we can make it clear. Right over here. Come over here. That's great. And to do that, I'm going to need to cast. And we got really good at that by way of Beat Saber the other day. Okay, so we're going to see if this works. In the meantime, and you know how to use this at this point because you've been trained.
No, wait, I see a button there.
Oh, okay, that means it's working. Okay, I just got to cast. Okay, hang tight. Immerse yourself in the matrix. All right. Sensory experience. Where is the MetaQuest something or other app? The icons are very
Roblox, that's not Roblox.
Oh, you see my phone, I forgot. That's the whole point, right? Okay. Searching for the headset. That. Right. Is that connected to the internet? Probably not. Let me set it up for you. Promise this will be right. I still see it already. Whoa, okay. It never gets old, huh? Okay, here we go. Connect to the internet. Gotta go here. Okay. Yeah, well, heck. Strangest class yet. We were going to darkness. What am I doing? I connect to Wi-Fi. Wi-Fi? Am I too secure? I gotta do the whole thing. No. This was once easy. Once upon a time. What's the song from the years? I once had a dream. Once had a dream. I need a text message.
I asked you about this morning.
Wait, what am I doing? It's so fun. Is it anything out of the ordinary, or is it just standard Christian fare? Did I get a text? Did I get a weird text?
No,
We can always use something.
Oh, okay. That's what someone who saw something else would say. Okay, send access code. That you call it. Send access code. Provide a valid email. Okay. I'll give you This is like understanding linear algebra. You look crazy when you do to others, but then when they're in on it too, they realize. Okay. Now let me know the access code that was sent to my mobile number because you will see my texts.
No.
No, it was just sent.
We can only see something for the headset.
You okay? Okay, here, read this number to me, please. No. Okay, hang on. Here. This one.
164226.
This is 426. I'm sorry. Okay, sign in. Okay, we're signed in. Nadia, can we do this? Please, let's do this. Nadia, por favor. Yes. Okay, are we casting? I would like to cast. Is that Nadia, por favor. It was made. Oh, wait, okay, we're connected to Wi-Fi. Nadia, por favor. Oh, I think we're getting it. We're getting it. Yes, it looks to be somewhere. Okay. Okay, going places. Yes! Welcome to the vector fields. Oh, this is wonderful. Alright, Evan, can you get the lights, please? Alright. So come toward me. Maybe I walk this way? Alright. Oh, okay, so you gotta X out of the stupid browser. No. So look at the bottom of the browser. No, not too far down. Can you get these two in?
Yeah, I'm looking at the bottom graph. I have
You should close the shades.
Yeah, so you see that little white line under the browser, that little white bar. No. That, okay, now hit the X. Good. So, no, up. Okay, and now with your thumb and index finger, pinch at the X to close it.
Right.
Your thumb and your index finger, pinch them together. Okay, excellent. Okay, so now, she's in a vector field. Careful, it's dangerous in there. Okay, so She is in our crouch actually, so we can get it censored. Okay. All right. So she is currently inside a vector field. Can anyone have a sense of where that vector field is pointing? Radially outward? Okay, and grab your left arm. Watch me. Okay, left forearm. Like you're looking at a fancy futuristic wrist computer. Isn't that how it works in the video game Fallout? Okay, I see.
Like grab.
No. You did. Okay, now tap on another field. That's what we do. Okay, so tap with your index finger. None of this is supposed to be obvious. We're still working out the kinks in the UI. Okay, look around. All right, that one's very similar. Yeah, I would pick the one in the middle. No, okay. And now look away from the control back. Okay. Okay, pretty colored. Okay.
Walk into the board.
So, yeah. All right, so you see that? So what does that vector field look like it's doing? Can you guys see the axes? Look down into it.
Oh, it's curling.
It's swirling, right? It's the water part from the child. Okay, yeah, want to pick another one?
Yeah, I can agree in a movie. Yeah.
All right. Maybe negative yx 0. That one's very similar. You gotta get. All right. I don't think you have to tap it.
Did I not tap? I think I
Not.
tapped it.
Oh, because it didn't look like it was changing.
Now it's not in a circle now.
Oh, okay. I see. Pick another one. There's a couple more. Okay. Maybe that trig situation, yeah. Yeah, tap all the way, so like literally walk into it. Press it, yeah. Okay, there we go. And now just look around you, yeah. Okay. Anyone else want to try it before we end this segment of the class? This segment of the class is called Get Busy, yeah. Okay. I'm gonna catch you for you. Thank you, Anita. Yeah. You survived. That in a day. Europe students of mine did. I'm not as quick as them as coding. But they're making it now so you can make circuits in three-dimensional space and like drag batteries and wires. Okay. POV. You're in a vector field.
Imagine the word being.
All right. So same thing with the arms on this. You remember? Yeah. Now tap. Maybe see YX. Tap it again. I'm not convinced that it rendered. Okay. Now field resolution and field alpha are fun little parameters. You can change the slider. So resolution is how many arrows per cubic centimeter there are. If you put too many, it'll be hard. Yeah. Okay. Now render type. Hit like 3. So now it's a lot of arrows, and it's also they're all red. Render type 2. The colors tell you the magnitude, and then render type 1, I think they're all white. So again, like you define a vector at every point. Depending on how many points you want to display this at, you can see them. Oh no. Okay, yeah. That's like the map of all the planes flying at a given moment. All right. Did someone say backrooms? I just got that vibe too from it. All right. Oh, maybe try that last one. Oh, I think we did it earlier. It was the same. Yeah. And that's the thing. It'll take too long to render them otherwise. But that's good. That's good. So hit the 2. Okay. See fewer arrows. All right. Is he tired? So this could be a dance that we do over some beat again because he's going.
Okay. Is that good?
Yeah, that's good if you're good.
Yeah.
All right. Cool. I'll have this at the end if anyone else wants to try it or go scuba diving or anything that we can do on this thing. I've recorded all the videos from the scuba diving trip in 360, so we can do that. And at some point I'll record this class in 360. I also have edges from last year recorded in 360. All right, so I'm going to showcase it again. We show a field. There we go. We can see the arrows. We're looking at the arrows, and we're seeing the directions that things point. Each arrow here, how do we define this arrow? Where does it come from?
The 0 back there.
Well, yeah, it's all relative to 0 vector. I'm with you, but like, how do we get? What am I saying? Each point. This is a vector value function, so each point is represented by a vector in 3 dimensions, right? So that one might look like. Can I do this with the VR headset? And this is totally unprecedented. So in 3 space, this might look like. Oh, it's weird because I have lag. Yeah. Wow, that's true. Yeah, I always see these arrows, they follow me everywhere, it's not just for the simulation. Yeah, someone help me. Okay, so X, but it's weird because I'm writing on the board, but there's lag because I'm viewing it through the cameras on here. Like, everything's a simulation. Okay, so this, for example, is a field in 3 dimensions, yes? Everybody good? Okay, POV. You like looking at an angle. So I can be the mobile camera. Wow, this is weird. Look, it's telling me something about boundaries. That's, I'm gonna go this way. There we go. All right, POV, you are, you're Vaughn. Okay, okay. Hi, Evan. POV, you're in the hallway.
Wait, what is that?
You're
Right?
I gotta get back to the circle. The storm is closed, it's Fortnite. All right, so that's vector fields. I hope this is a motivating beginning to the topic. We are going to do some calculations for vector fields. The main thing, maybe I can one more thing, is the following. While I'm in a vector field, what I'm interested in is, like in real life, I'm subjected to forces. And what I would like to do is figure out how much work is being done on me by those forces. So we have field, another word for force in this case. Any physics thoughts here?
Yeah.
And what else do I need? What else do I need when I am in a field to get work?
Distance.
A distance, or not a distance, but a
Right.
displacement. I need a path. This line, wow, it's pretty cool. Never done it this way before. We want to make it so that you could draw paths here, but this is a path, and I'm going to walk down this path subjected to this field. Okay, do you all see that? So how do you find the work done on you by this field, which is the arrows, when I'm going along this path from here to here?
You have to dot the first part of the distance.
You dot the force with the, remember not distance, but with the
Displacement.
displacement, exactly. So at every little point here, right, I am moving, yeah, I'm moving here. This is my field. And I'm going to do field, which is that purple arrow, dotted with my displacement. What direction is my displacement if I'm traveling along that white line? This way, right? So it's purple arrow dotted with my thumb, right? Then it's that purple arrow dotted with my thumb. Then it's the blue arrow dotted with my thumb. Along the path, you are doing the dot product of your field and your displacement. Does that make sense? Okay. Now, along this path, is the field doing work on me? It kind of looks like it is, right? These vectors are not all perpendicular to my path, right? But let's pick another path. I've never done this demo this way before, so I'm actually having a really fun time now. Okay, if my path is like this and my field is like this, you think there's a lot of work going on or not?
No.
Yes.
Remember, what's working? Is it?
Not a lot of.
Yeah, but look at my path. My path is exactly in the direction of the field.
Parallel. That means it's maximum.
It's maximum work, exactly. Okay, and then if I was, I don't know, like here,
Perpendicular.
perpendicular, hold up the story, right? In fact, actually, what kind of path, it doesn't have to be a straight line, what kind of path would have zero work done to it if this field is radially outward?
It's gradient.
A circle. A circle. Okay, let's pick another one. This field is, yeah, linear, we said. What about this one? This one's very curly. This one is, anyway, you guys get the idea? We're interested in how paths and fields interact with each other. We're going to do it in 2D, but maybe 3D looks cool and reminds you that this can be cool. Are there questions before I stop being cyborg and Christian? Questions? Yeah?
Could you like do POV level with this one? I just want to see how.
Oh, it's really fun. Well, so the reason this is happening is because projectors are not flashing one image at a time. They have a color wheel to give you the R, G, and B image, and this just taps into that phenomenon because of the shutters. But you do get, yeah.
Like you went to Disney, like,
Oh yeah! Oh, this is awful. Yeah. Someone wants. Oh, I can look at the phone. Is this how you feel when you look into a pizza?
yes.
Wow, we're not gonna. All right, so if you guys want to build an infinity mirror, we could do that in my office. All right. I'm good? Are there questions? Are we gonna do some calculations now? But are people good with the stuff? Okay, cool. All right. Wow. Oh, welcome back. Okay. All right. Very cool. Okay. Thank you very much. All right. And did we get the lights here? All right. Oh, this was fun. This worked better than I thought it would. Okay. So fundamentally, at every point, we have a path and we have our field. Our field's going to be orange and our path is going to be, I guess it's going to be white because I'm running out of colors here. Okay, here's our field. Arbitrary field. And in this world of this field, which we'll talk about in a moment, I have a path. Okay. And along this path, and that is going to be something that we're going to say a lot, along the path. Along the path. What's an easy way to remember along the path? C. The path is called, we're going to call the path C, which is Spanish for yes. And what else? But along the path, ATP. Do you want to screw with biology? Let's reclaim ATP. All right, along the path. We have our field. Our field, do we agree it has two components? And these components are functions of x and y. I'm going to call it m of xy and n of xy. Some books call it p and q. I don't like that, but that's just because I wasn't taught it that way. Maybe it's a bias thing. Okay. And so at every point along this path, I'm going to do field. So this is field at this point, dotted with what?
You're dotting with the.
Oh, yeah, there's my colors all kinds over here.
So your field, your displacement vector.
What's my displacement vector at this precise point?
This at that point on the C. Because C is
Yeah.
arbitrary value.
It's at that point, but like what direction does it point in?
Yeah.
You're telling me that, so my path is moving this way?
Yes.
No, it's parallel.
It's parallel to the path, so what's the word for that when we're along the curve and we're going to tangent. This is the unit tangent vector at that point. So f dot t hat here, right? And then what am I going to do here? The field here, whatever it is now, dotted with t hat over here. The field over here, dotted with t hat. Right? Here's my tangent vector, here's my tangent vector, tangent to my path. At every point, I'm looking for field dotted with tangent vector. So I'm doing f dotted with t hat. And what am I doing to get the total work done along this path?
Integrating from your displacement.
Integrating over the whole path, yes. So that path is called C. And I'm integrating along that whole little path, so ds, s for the little arc length. Okay, this is the work done by the field on me. Is everybody good?
What is a little
We're going to sort that out, fun, yeah?
So how do you find the balance with displacement? Like, is it just the length of the path?
Oh, rarely do we do it this way because t hat ds, if we're moving along the path, right, and we're taking little steps, this is the next part, Vaughn, you unlocked that already. We're making a tiny change along the path in the x direction and a tiny change in the y direction. What do we call those?
dx dy.
Dx, dy. So t hat ds is dx, dy.
But it can be dx dy dz sometimes.
If we're in 3 space, yes. Dx, comma, dy. This is a tangent vector. This is a tiny change in the x direction, tiny change in the y direction. What is the slope of this, of a line with this vector? What is the slope of this vector? dy by dx, rise over run, right? So it stands to reason that this would be that. Does that make sense?
A little bit.
All right, hang tight.
So let's simplify that function now.
That we better do that. So that's going to be now f dotted with dx dy. Well, what's f? It's got two components, right? M and n. So I should also write this part out and expand it. This is m n dotted with dx dy.
So does C become a factor as well?
It does not. That's a really good question, Lauren. I mean, no, I'm sorry. No. Okay, I keep bouncing back to C guys. All right, so this becomes m dx plus,
Add dy.
you got it. This is the work done. This is called a line integral. Why is it called a line integral? Over a line, yeah, over a path which, yeah, this is a line too, even if it's not a straight line. Okay, m dx plus m dy. Last year, I needed a way for people to memorize things, so I asked ChatGPT to write a song using a transcript from my lecture, and then I gave it to Suno, and it made a country song, and it was awful. I won't expose us to that, not when we have such lyrical talent in this classroom. But it had a bit with m dx and m dy. Okay, biggest thing here, where are we evaluating this integral? Where are we summing? Along the line, along the path. Along the path. Last semester, it was always one of these buttons on call to say ATP. Very important. Okay. Train myself to ask for treats and go to the bathroom and integrate along the paths. So this is the work done as a concept. We haven't done a problem, but as a concept, does this idea make sense to people? Fun. Oh, okay, cool. Now you had a question. Oh, that's cool. Did things clear up a little bit from the T hat DS? You can prove this. We're being a little bit quick on that, but it is a thing. All right. So let's do a problem and get our hands dirty so that we can see what this actually is. I didn't bring words today. Screwed up.
As it moves on to okay, it's length.
We're going to go over the process of how to do these. So example 1.
This is actual metric. I can see your yeah, TS
Find the work done by the field F equals x squared y, comma, x minus 2y. It was an arbitrary field along, because we need our path, along the segment of the parabola y equals x squared from 0, 0 to 1, 1. We will go over how to solve these kinds of problems. We'll do this one together and outline some steps. It's my hope that I remember that. Let's sort this out. Are you good? Oh, because you normally don't sit there, so I was afraid. What's up?
No.
Okay. Okay, so step 0. What is usually the flavor of our step 0? Draw. Then we'll write down stuff. Okay, so let's draw the path. Okay, what's our path? Piece of the parabola from 0 to 1. What does that look like? Use your hands. It's cool. Yeah, oh yeah. Okay, this point is 0, 0. This point is 1, 1. And this is our path C. All right. That's step 1. Does this make sense to everybody as our path? We're starting here, and we're ending here. Okay, step number 2. All right. Noah, this is what you said now. Write out the equation, right? Write out the line integral. Okay, help me out here. What is it going to be? W is equal to?
Integral of C
over C of? M dx plus n dy, or f dot dr, we can go from all sorts of places. Okay, what does this look like more concretely? What goes in here?
as is x squared y.
X squared y, yeah. x squared y dx plus x minus 2y dy. And this c means what? Along the path.
Wait, I'm the mathematician,
Huh?
but you know, you see summations and you're adding,
Huh?
you can always split them.
Oh!
Or,
Not quite. Let me explain why.
or.
Let me explain why. Is this a two-dimensional integral or no? Hi Lily, you want to answer that one? Is this a two-dimensional integral? Oh, well, there's two variables, yes. But the place where we're integrating, is it two-dimensional? No, right? Why is that? It's a line. A curved line still counts as, if you lived on this line, all you would know is this one dimension. You can only go in one direction along that line. So this is a one-dimensional integral. But we've got two variables, you guys. How could it be that we're along one dimension?
Wait, because y is equal to x squared.
Ha, you're gonna say that?
I was gonna say something else.
Say it.
What if you let x equals t, y equals t?
Yeah. That's what we're gonna do.
You stole my nachos bread.
And then you divide dt and then you multiply dt.
So that's the bit, if we're along one dimension, something is quote unquote degenerate, something is dependent on something else. We've seen that in linear algebra, but it stems from many more sort of ideas. Do you have a question? Oh, I think I had a question. Yeah, you're gonna know.
No.
No, I was looking at Nolan actually.
Oh.
You good? Okay. Okay, so yes, this is one-dimensional because x and y are related. Now there are two ways we could do this. The first is just to write x in terms of y or y in terms of x. I'm going to introduce a way that is a little bit more generalizable, and it's actually what David said. We're going to parameterize in terms of, you're going to look at it and you're going to see, well, Christian, why can't we just say y equals x squared? That's fine too. But this will scale better. Very few things scale well in life. All right, step 2. We're going to enforce along the path. Where did I put my ATP situation? Enforce ATP by parameterizing, or is it parameterizing? I must have misspelled it if that's the way it is, the path and bounds. Okay, so our path C, let's say that x is equal to t. All right, Noah, what is y equal to?
X squared, t squared.
T squared, yeah, okay. What are the bounds on t along this path?
We're talking about the x bound, so 0 to 1.
0 to 1. So, okay. So that's enforce ATP on the path and the bounds. Step 3, you gotta enforce ATP by parameterizing the differentials. dx. If x is equal to t, what is dx?
1.
dt. If y is equal to x squared, what is dy in terms of dt? 2t. What am I missing? dt. Well done. Okay. Where else do we need to? Oh yeah.
And then we conclude that x equals t and y equals t squared. Like why did we conclude this?
Oh, it's our choice to unify everything under a variable. Why this? What else could it be? Let's try another example. Oh, that's the usually it kind of just looks right. This is annoying for me to say. Yes, I agree. Y is equal to x squared, right?
Yeah.
So your instinct might be to say, okay, wherever there's a y, change it to x squared and make everything in terms of dx. That's this, but imagine that our path was like a circle. In the case of a circle, it's hard to write x in terms of y, but you can write x and y in terms of a parameter t. Right? So this is doing that everywhere. I'm doing this here. even though it would be the same as doing it the other way, because doing it in terms of t will scale well to other.
So we're just setting x equal to t, since y equals x squared, y equals.
Yeah. Whenever you can write y in terms of x, just make x equal to t and y equal to that function with t. It's the same. But if you feel comfortable, you can do the same thing and say instead y is equal to x and solve everything for x. So this procedure would work that way too. But this is the more general way. All right, more questions, you guys? Okay, what's the last thing we need to write in terms of our parameterization? We've written the path, we've written the differentials, what's missing?
Here it is.
We got our bounds too.
Let's plug it in.
We're missing something.
Oh, we gotta put f in terms of
The
t.
field, yeah, so next step, step 3, or step 2, step 4. Write the field in terms of t as well. And 2. Okay. So m, the x component of the field, what is it? In xy land? X squared y, right? What's that look like in parametric? T cubed, right? T squared times, oh wait, actually, is it t cubed? T squared times t squared.
Ooh, it's a square.
You know why, right?
Yeah.
Alright, WHY. Alright, yeah, because we got so many letters and words sending off here. N is x minus 2y, what's that in parametric land? T minus 2t, or am I missing? With feeling. Alright, that was a little more feeling. Cool. Okay, step 5, bring it all together and plug it in. So let's do that. Step 5, bring it all together. Okay, let's actually plug it in. What does our work look like now? Originally, it was x squared y dx plus x minus 2y dy along the path, ATP, very important. What does this look like if we plug in all of these constraints? Integral from 0 to 1 of x squared y becomes t to the 4th, dx becomes dt, plus x minus 2y, which becomes t minus 2t squared, right? dy, what does dy become? 2t dt. All right, what's left? Got a bunch of terms of dt's in them, what can I do? Yeah, combine them, so we got t to the 4th plus, and then you want to distribute this up, 2t cubed, 2t, oh wait, should this be, no, we're good, plus 2t squared, yes, 2t squared minus 4t cubed dt. Is this an integral we feel capable of solving? We're back in single variable now. Wow, I missed that. All right. If we solve this, we get the luxury of saying ... Thank you, Chapel.
And 215s.
Yep. Yes. That was quick. It's like when you order food and it comes back too soon. You're like, you did not have time to make this correctly. Well done. Okay, cool. You just in your head.
No, I looked at it, looked at the measurements at the time, forget it.
Oh, I forgot these were already posted. Thank you, Evan. All right. That's good stuff. All right. Yeah, like we know you guys can do the actual work, so we're not going to dock you points if you get like a minus 3/15 or something. Although you should simplify that fraction, minus 3/15.
I think he should have taken credit for it. You should think, yeah, no, I solved it
Okay.
in my head.
For some paths, the need for parameterization is more obvious. For this particular example, you can imagine that we could have just written everything in terms of y as a function of x. If you were like this in your world, I'm going to, in green, which would be very, very glowy if we were in glow-in-the-dark class. Let's do it now the way that Andres wanted to, because his instincts weren't crazy. Instead of doing it all in terms of t, oh, Sylvine, you have a question?
How
How do you know that x always equal to t? Why
Aha.
not like
The only reason I'm doing this is because y is directly a function of x. Along our path, right? Along our path, y is equal to x squared. So, y and x are like directly, explicitly related. But let's say that our path was a circle of radius 1. How do I write x as a function of y along a circle of radius 1? Yeah, square root of a bunch of crazy stuff, right? What's an easier way to write a circular path of radius 1? Parametrization. X is cosine of t, y is sine of t. So then we could unify everything in terms of t that way. We can do another example with it, but does that make sense? Like,
Yeah.
we want to unify it under a variable. T is fine here, but let's do it the way that Andres was saying. Okay, Andres, what was the BS that you were calling me out on? What did you say? Why do we care about T? Ah, you know, it can be BS. I want it to be BS.
It could be.
All right, so what you're like, yeah, what do you want to do? You want to say that y is equal to x squared, right? Okay, so what's dy? 2x? 2x dx? How can we write all of this in terms of x then? Yes, x squared times x squared times x, which is x to the 4th. What about this one? X minus 2,
No, it's squared.
x minus 2, x squared. Notice, what's the only thing that's changing? This was t to the 4th, now this is x to the 4th. This was t minus 2t squared, is now x minus 2x squared. dy is 2x dx. Oh, what's dx? dx is just dx. Oh, what are the bounds on x? Yeah, does that look vaguely familiar? Okay, so that's all of this, and then what does this integral become if we go on in terms of x? X to the 4th, x minus 2x squared, this is minus 2x, x to the 4th, x dx, dx, dx. Same idea. This is not like an x that is wrong. So it's a choice. If the parametrization helps, great. If this helps, that's fine. But if you write it all in terms of x, realize that there are functions that are not so easy to write y in terms of x. It's easier to just bring both variables under a parametrization t. Does that make sense to you?
Yeah.
Okay, cool. More questions? All right, as usual, we're doing fantastically on time. Let's keep going. The path can range from pretty curve to a bunch of pretty little lines. So let me do that here actually. Right? Maybe I'm going from point A, or did I use big A? I used big A and big A. Yeah. If I'm going from point A to point B, I have some field defined everywhere, I call F. This is my abstract field. You've seen it now in three-dimensional space, which is really cool. And I can get from A to B in any number of ways. One way, maybe I go this way, a path C1, and then I go this way, a path C2, right? So if I ask you for the line integral along this combined path, what would you do? You'd break it up into two integrals. One along this path, one along this path. Does that make sense? Because these are easy to find. What's y on this path?
0.
Well, I mean, it's more than 0. It's 2. But what is dy along this path?
0.
So you can see how the line integral is cleaned up, right? Okay, what about this one? This one, x is maybe 5. So dx equals 0. What are the bounds on y along this path? 2 to 7. Okay. Same with this guy. What are the bounds on x for this guy? 1 to 5. Those are just numbers that I invented for this example. Does everyone see the idea? So if we had a combined path, this is you walking along the force field this way. C1 and C2. All right. And now, here's the fun part. Isn't this all the fun part? This is a path that I can take from point A to point B. What's another path I can take from point A to point B? I could take the hypotenuse, oh, I remember that from an AP English exam. It was very embarrassing, but I don't really have much of a sense of embarrassment. And I went up to my teacher, and there was this exam question on the AP test, and it said, does this explain the, and I'm like, what does this word mean? And I read it to her. Hypocritical. Hypocritical. And she looked at me with a weird face. She was like, Christian, you know this word. Hypocritical. And after the test, I'm in the bathroom or elevator, I don't know, wherever it is that we have our teacher's thoughts. Hypocritical, I know this word. I was pronouncing it wrong. So I'm like hypotenuse, and now I'm like hypotenuse. Okay. So is the work done along C3 the same as the work done through C1, C2? Is my work going this way, the same as the work going through these people? Yes. Some say yes. Some say Some would even go so far as to say no. I sense a lot of beef in this class. The beef matrix is something that I can talk to you about in office hours. It is a total paradigm for any workplace or group situation you encounter. But we're not going to do that now. What the heck was I talking about? Get out of it. Some of you say yes, some of you say no, some of you say maybe. I get to draw on the fact that I'm in close proximity to a chemistry person. What's a state function? Yeah, all right. I know Chem Alley did this by like dancing around the classroom or something. From a conceptual standpoint. Does it matter how you get there? For sometimes it doesn't, right? For like state functions in chemistry, something. Sometimes it does though. Let's say the force that I'm talking about is friction. And I'm trying to get from here to Leiden. And I'm going to push this box, as Patty Christie would say, this box. I'm going to push it. I'm going to get to Leiden this way first. Here. Friction. And then, okay. Is the work that the friction did on me the same as if none of you were here, because these chairs wouldn't get in the way, and I went, yeah. No. Tell me more. Okay, you guys got this. If it's starting to look like I'm dumbing it down too much, that's a good sign. What's that? What'd you say? Does it depend on the path? Yeah. For friction it does. Now here's another example. Work done by gravity. Tell me more. All right, you will in a second. How much work is gravity doing on me when I go like this? Is it positive or negative work? What direction is gravity pointing? And my path is? So work done by gravity is? Negative. Now, is it the same when I go like this versus when I go like?
Yes.
You think it's the same or different? It's the same. I forgot what question I asked. That's why I asked. Okay, it's the same. Exactly. So all of this to say that work is sometimes half independent. Sometimes it is half dependent. What does it depend on? It can depend on the path. What did it depend on? The field, yes. It depends on the field. I'm picturing, I want to write this with AI. It is an app that when I speak, each word live as it's being heard gets conveyed as an image. So it will give you the clown. Depends will give you the adult diapers, and I don't know what we'll go after, but I just had this fleeting thought just now. Okay. It depends on the field. When the field is such that the work is path independent, the field is called, it's called a conservative field. All right. Sometimes it is path dependent. What is that field called? Yeah, I was about to say, yeah, you gotta go political with it. F is non-conservative. Okay. Aside from politics, what else can we dig into with the etymology of this? Conservative, non-conservative. What's that word conservative come from? Conserves. Conserves. So tell me more about conservation. Conserve. Not quite constant, but oh, I guess yeah. Like the work is a constant quantity no matter the path. Yeah. What do we think of as being conserved in physics? Energy, you can get it back, exactly, right? That's it. Oh my God, that's a really good point. Okay, if gravity does negative work on me going this way, what happens if I go in reverse? Ha. What about friction? If I'm going like this to Lila and then I come back, I work twice as hard, right? There's a reason I prefer rock climbing to lugging, boxes. Boxes. Okay, that is a Patty Christie thing. I've known Patty my whole life, not my whole life at MIT, and that's something that I've gotten from it. I feel like I've absorbed something from it. The other thing Patty Christie does that I like is she always sounds like she's just a little bit annoyed at the material, and that resonates with the part of you that is also annoyed at the material. I try to do that too, but sometimes I get too happy, and then you don't like me because like, what the heck, Christian, I don't like this yet. I understand. The other thing she'll do is when she says hi to you, you don't know if she's happy to see you or not. Hey, Andres!
Yeah.
Is that ironic? Is that, and there's a really funny story. It's true. Yeah, there's a story there with how I adopted this not unknowingly, and then I used it on somebody not knowing I was using it. And for more, come to office hours. I think if Ken Alley's doing office hours today, I'll be doing office hours because she's coming out. Anyway. Okay. Okay. We're going to unlock why this is called conservative. If the field is conservative and my path is a closed path, my path from A to B is closed, how much work am I doing?
Zero.
Right? Up here plus down here goes to 0. And now again, dragging a big box and friction toward Lila, a closed path here, the work done if A is equal to B, is it 0? No. Okay, I need to formalize this with math a little bit, but I'd like to check with you guys, as we usually do, does this make sense? Are we okay? Don't have to be. Yeah, did you have a question? Sure. Awesome. What if I whisper the rest of the class? ASMR calculus. Oh, the internet is a rich tapestry, man. At one point, I was, I don't know where I ended up, but there was a video of a man. It was personal attention ASMR. And there was a man who was chopping carrots for you in his carrot restaurant. And he's whispering to you, and he's chopping carrots. And I didn't know what I was supposed to feel then. Yeah, and the question is, how did I get there? That's the SAM algorithm. Okay.
How would that look on the circle?
Oh, in a circle?
Like, yeah.
Well, for that, if it were a circle, you would do x and y as functions of t. You parameterize.
You can't piecewise a circle.
Yeah, you could with a lot of pieces.
Oh, that's true. So you want straight line pieces for those?
Yeah. Yeah. But if it was a closed path and the field was conservative, even if you made it out of a octagon or.
By that point, you know it's not going to matter.
Is correct. All right. We need to talk about criteria that make a field conservative. We need to talk about some of the mathematical notation. So let's do some of that. First off, if f is conservative, then the path integral for a closed path. We're about to unlock some very pretty notation. A closed path line integral. Guess what kind of little decoration it gets? It's Christmas.
Circle.
Little Christmas wreath, yeah. Right? Ho, ho, ho. Oh, right. Or maybe better said, you better watch out. All right. F dot dr is equal to? 0. This is called path independence. And one more thing, if the field is conservative, and we can prove this, but we haven't got time to, but come to office hours, we can mess with this a bunch. If the field is conservative, then the field can be written as, okay, all you chemistry people, because I deal a lot with chemistry in my life, because of the chemistry in my life. That's pretty good. All right. Is the following. For Coulomb, for the whole thing with the static charges and you bring them close to each other?
Q1, Q2 over
Yeah.
F is equal to, whoa!
So wait. What were you plotting in chemistry? You were plotting Coulomb, but what were you plotting? You weren't plotting the force, you were also plotting the...
energy.
Huh? The potential energy, yes. Do we know if electrostatic attraction is conservative or not conservative? Loyan knows. Loyan thinks
It's
that
conservative.
it is conservative, yes. And as it turns out, all of this mess of alphabet soup that I'm throwing out here coalesces into one line. If the field is conservative, it can be written as the gradient of a little function f. This is called the potential function.
Oh, we can solve the potential function.
You can solve for the potential function, which is a pain in the butt,
It's
but
like, is that it's like a
yeah, it's little f,
integration.
yeah. If the field can be written as a potential function, if the field can be written as the derivative or the gradient, right, of a potential function, it is conservative and all of these principles hold.
But if there's no potential function, does it mean it's not conservative?
Oh, you got me going with the mathematical arrows in the directions. I'm supposed to be able to give you a good answer to this.
No.
Give me 13 seconds.
That's not how you should look at it then. Not how
No, it's not. It is how you should look at it. It's how I should look at it before I walk into a class. So falling with style, right? It should go both ways. I think the arrow goes both ways. Does anybody know more and has looked into it and wants to disprove me? Go ahead.
Where is my
Okay. Because this wasn't a rhetorical point. But for our purposes, getting by, this will do. If you have a potential function, it's conservative. If it's conservative, you should be able to find a potential function. Right? Later we'll ask Claude to disprove everything during the
that
workshop.
actually makes sense because
You all saw that, the Jacobian conjecture, which we could talk about too. Claude disproved it in, during the World Cup game. It won't affect when you get on the final, in fact, the Claude disproved something.
you could potentially,
Yeah, Leanne, what do you make of it?
if this, taking this guy.
All right, guys, we need to do the fundamental theorem of calculus. We have 3 fundamental theorems in this class. There's no such thing as a stupid question. Nothing is supposed to be obvious. Nothing is supposed to be interesting. The fundamental theorem of calculus in line integral land is the fundamental theorem.
Line integrals.
Yes. How does he know what I'm going to do? What am I going to eat for lunch? I really want to know, so I know if to take my acid reflux pills. Fundamental theorem of line integrals. If the field is conservative, if f is the gradient of a potential function, then the line integral from point A to point B along a path C
It's equal to.
How does he
No,
do it?
that was.
You gotta whisper, you do the ASMR, so I think it's actually coming
Equal
from me.
to the Green's theorem.
That's, no, not your Green's
No,
theorem, okay,
no.
you skipped the page.
5B when it's 5A.
Aha, well, 5, we're gonna call it little f, but yeah.
Oh,
This is equal to, no integral. This is equal to the potential function at the endpoint minus the potential function at the starting point.
Oh, because you plug in f as grad of f, and if you're integrating each little piece, you
Exactly,
get that
this
part.
multiplies out, you could prove it.
I see it.
All right, such is true, such is true. If the path is closed, then f of b and f of a are the same, because b and a are the same point, and this goes to 0. Very cool. This is fun stuff. Again, the path, the work done going through both of these directions is not the same as the work done along this direction, unless the field is conservative. If we can write the field as the gradient of a potential function, then we are in good shape. This is called, again, the fundamental theorem of line integrals. I call it the Declaration of Independence. And I usually give people like a scroll in class that has the Declaration of Independence. But here we are. Okay. Conservative fields are sometimes called gradient fields. Wonder why? Questions? Hey, what's up?
Can you prove it?
Yes, but really quick. If the field is the gradient of a potential function, then this is df dx, df dy, dotted with dx dy. Df dx plus df dy is the differential in f. And if you integrate that, you get the f's at the endpoints. But this is where you want to be. Okay. You may have questions for me. Christian, what's going to be on the final? Christian, maybe this is a better question. How do we find the potential function? I'm going to answer question number 2 instead of question number 1. What is that? Oh, no, that's for next week. But no, the final will probably be 6 questions. Someone during office hours helped me come up with that. I forget who it was. All right, you can erase here. People are good? Yes? Okay. Sometimes you're going to look at the field and be like, yeah, that's the gradient of something. Sometimes it won't be so straightforward. So here's a question for you. Is this field conservative? 2x, 2y. All right. Raise your hands if you think this is conservative.
Let's do it. Oh, yes.
You do think that way? Okay, so why? What in your mind said, oh, conservative?
I was just explaining this to 2x y.
Sure, go ahead.
Okay, well, if we treat that as grad f, hypothetically speaking,
Yeah.
then that means we know the partial derivative of f in respect to x is equal to 2x.
So what function has that?
Well, yeah, let's solve for the function.
Okay. You can do this one in your head. Yeah.
Yeah, and maybe it's x squared plus y squared.
Okay.
There.
Hey, that's not bad.
But what if it's a more complicated function?
What's this more complicated? That's exactly the point. Oh, and also this could be plus 73. Or
Yeah, plus a c.
Or anything.
This thing, yeah.
Oh, right. This is as easy as it gets. This is
X
the.
equals y squared equals 6, 7.
Aha.
How did this prove it's conservative?
Because the gradient of this function is what? And that's our field. So this must be the potential function that gives you
Could
the
be.
field.
Well,
It has
if the
potential
gradient
to
is
be so.
conservative,
Well, if the field is if the field is the gradient of this, then the field is like if you can find a function whose gradient is the field you're given, the field is conservative.
5.
That's a fact.
Yeah.
Just having it.
If it can come, if it is the if it can be the gradient of something, then it's
2
conservative.
hours to do 5.
Right? If this can be written as the gradient of a function, then that's the
This one's
function that gives you this.
Oh,
Oh, let's do it.
Wait,
What cannot be a gradient field? Let's say.
Let me cook.
What about this one, you guys? Yeah, go ahead.
How about, why don't we just do 2x, comma 2y plus
for this
x?
problem. They get points for if they say he's short.
Okay. What's this the gradient of?
Christian is short.
Yeah, maybe you should work it out. Because then, like, then it'll, like, see what I'm saying? It'll,
Yeah.
His objective
So,
is
in general, on this eyeballing isn't going to serve us very well for too long.
right.
We need a systematic way to come up with the fact that the field is conservative or not. You agree that non-conservative fields have to exist, because like not all paths are going to give us that independence. So that's what we're going to need to talk about. Now, I realize we hit time, but I also realize there's a question in the piece set about finding the potential function. The Green's theorem you are responsible for because you can solve that. Do you remember what part of the piece set that problem is on? Yeah, could you? And let me know what part.
What part? Okay.
There's one where it says, yeah, find the potential function.
I'm on it,
Okay.
Find the potential function. Potential function. Yes, 4b.
And that's the only part that says find the potential
Yes.
function? Let me see what else for.
So potential
Or
function
is-
is just like
Okay.
a path independent.
Show that.
Oh, okay, not for nothing, but
It's
I
just like-
will keep this one on the P set because this is a field that you're all familiar with by way of physics. So if in doubt, look it up. That one in particular. Don't look up the process for, so let me clarify. You don't have to derive the potential function, you can look it up and use it.
This is E and M.
Or it's gravitation, is the problem.
Think about what Amit told you.
Yeah.
Think about what Amit told
And actually, you guys know gravitational potential versus gravitational force, right? One of them has a 1 over r, one of them has 1 over r squared. That sounds like derivatives added in more word. Okay. All of that being said, have a wonderful weekend. If you come to Chem office hours in the SG, I'll probably be there. We have